Very much for that introduction, and it's really very pleased to be here, and a great privilege to give this lecture here in Australia. I apologize because of my accent, the Latin American accent. And well, this is the McEllhiney, it's difficult to pronounce, McEllhiney lecture. And well, it is supported by the National Groundwater Research and Educational Foundation. And this series of lectures are in honor of William McEllhiney. William McEllhiney was the first founder, president of the National Groundwater Association. And the lectures are supported also by a grant of Franklin Electric to the National Groundwater Research and Educational Foundation. Few more words about William McEllhiney. He was a civil engineer and a groundwater contractor. And was one of his objectives and the association as well is to serve as a clearinghouse for groundwater knowledge dissemination. And it is in that direction that I am giving this talk. So I'm Carlos Molano, and I devoted my professional life for groundwater to both for consultancy services and also given some classes at the university. And that's the title of my lecture. This is my lecture number 20, Groundwater Spreadsheets. And you can see that, well, it is an efficient and practical resource for solving groundwater problems, environmental and pollution problems. This is the general outline of this lecture. There are 9 topics, and of course, some of these topics are interrelated each other. And let's begin with some background, motivation, and the objective. And let me begin with a phrase of a comedian and BBC writer: as much as oil and water, our lives are governed by Excel. And well, that's true. Everybody use Excel from simple arithmetic calculation, probably just to fill some blanks. And also some people use it with very complex programming. And you can see that it is a simple and practical resource for hydrogeology teaching. It's a wonderful resource really for teaching, but also for research and practice. So the objective of this lecture is just to share with you some of the things that I did with spreadsheets. And I try to keep that spreadsheets as simple as possible. And I will present without any programming. Well, I use programming with Excel, the VBA, the Visual Basic Application, mainly for my one semester classes at the university, but since 20 years ago, mainly for continuing education courses where you have a wide variety of attendance, geologists, students, engineers, biologists. Even I have had in the past environmental lawyers, medical toxicologists, and very recently anthropologists. So some of them do know nothing about programming. So I use in the more simple way just to fill the cell in the spreadsheet, copy and paste, and obtain a solution. So let me begin with this very simple problem. And this is, well, 2 wells. It can be here some potential source of contamination. We have a lot of problems with service stations in Latin America. And probably here located some wells, some receptor. Also, we have a lot of problems with septic tanks and can be, well, any source of pollution, for example, at some industrial facility. I use metric and English units, but as far as you are consistent, here you have, well, the slope, and this is, if you have just 2 points to measure the water level, well, it's very simple. There is just a line between these 2 points. And if you use the spreadsheets and choose what's the linear trend, well, that's the simple equation. And yeah, let's move forward. And if you want to know, for this simple problem, the head every 10 meters, well, you can replace here in this analytical equation. But another way is to solve that, probably not too efficient way, is as follows. Just that the head can be the mean value of the neighbor head, just to obtain a numerical solution. Copy and paste, and of course select the proper values for the graphic, the X and Y, or the X and the head. And it's very simple. And if you choose iterative solution procedure, that's what you obtain. Again, the same line and with the head values. So that's a numerical solution of this line, and actually is the solution for an homogeneous confined flow. And well, we have not talked about Darcy, but for this simple example, you have here the analytical solution, this equation, this linear equation, and that numerical solution. Now, some overview of Darcy's law, very familiar for all of us. And one way is to take a sample for a borehole and send it to the lab. There are many ways. That's one way to explain Darcy's law. And that sample just a refreshment, put it in that device in a permeameter, pass a flow through that cross-sectional area and measure the difference in head in that length, and that's Darcy's law. Very often it's convenient to express that equation per unit area, and this is the specific discharge. And if you have the effective porosity of this sample, you get the transport velocity. So in our spreadsheet, you can recreate this experiment. And here I use green colors for input and yellow colors for output. And you just give values here of the head, and you obtain the discharge through this permeameter. But there are some other ways to do that, and one is to pick that line with the mouse, pick any of those 2 points, and just drag with the mouse, and so you can obtain here the discharge rate. So it's also not too complex, and it really is a wonderful tool to understand not only Darcy's law. And here you can see that it works for Excel 2003. And when Excel 2007 came out, well, almost all my problems, my courses were in Excel 2003, and that property doesn't work in Excel 2007. So imagine my frustration when all my problems were in Excel 2003. But there is always a solution, and it's really a good solution. It was for Excel 2007, 2010, and you can download this into manipulate points or charts. So for the same problem, you choose the graph, here manipulate points on the screen, on the chart, and you get that window. Choose that specific graph, and any of these 2 points, point 1, for example, and move it that point. So it is also a very nice feature just to understand, in this case, Darcy's law. It works pretty well. And continue with our first problem. Well, you can calculate the transport velocity for a given hydraulic conductivity and effective porosity. So you can measure, very simple, the travel time from this point to this point, and is 1,000 days, near 3 years. And the travel time can be a measure of a risk. If you deals with some coliforms, probably 3 years, the risk is low. If you deals with some hydrocarbon compounds, can be medium risk, but some persistent contaminant, like some pesticide, probably is a high risk. But let's do the same, but for a fixed delta time, just to recreate particle tracking. So you fix the delta time. This is the same problem. And you update the travel distance for this delta time. That's a very simple equation. And is this yellow point? So again, if here I update the x, here is the delta time. So by pressing F9 in Excel and choose the iterative solution, you can see there the movement of that particle. So this, for this simple equation is, well, it travels constant velocity. And you, of course, obtain the same answer, 1,000 days here, or something you have to, okay, here 1,000 days. So you can, in this few spreadsheet, just to represent the analytical solution of the head for one-dimensional and the numerical solution also, but the advective transport velocity here is a semi-analytical procedure. But now let's see in an heterogeneous media that can be this special device permeameter. And if you have different type of soils, this is Finite-Difference. Well, the head in each cell is not the mean, but is a weighted average of the neighbor cells. Here you have the formula. So just copy and paste for this very simple example. You have this, the same specific discharge, the velocity, and just one additional row to see where is located that particle. And you can track that particle exactly in the same way as the previous spreadsheet. So let's make the solution, and you just press, well, here there is an horizontal head, so there is no flow. So let's begin with the difference in head between these 2 points, and that's the first iteration, the second one, the third, and after 4 iterations for this simple problem, you get the solution for the head. Now, let's track that particle here every 120 seconds for these experiments. Okay. So, well, there is visually a low velocity of that particle. Again, low velocity, of course, depends on the gradient and the porosity. But let's see here. You can see that it increased the velocity of that particle, and then, again, low velocity, well, compared with the previous one. So again, here is just a single formula, just an arithmetic, algebraic formula, copy and paste, and that's the way it works, all the models. Even MOFLOW, that's the principle of particle tracking, and also the finite-difference solution. So that's why it's an excellent resource, especially for teaching groundwater flow. Now, hydrological cycle can be used for groundwater management, for climate change analysis, sustainability issues. And, well, this is the hydrological cycle. Well, you can find many textbooks, the rain, the surface runoff, sulfide retention, infiltration, groundwater replenishment, interacted with the environmental, here some spring, well, here also connection with the surface stream, with wetlands, regional flow, evaporation from seas or from the sea or lake, evaporation from surface water bodies. Yeah, well, if you have a shallow water table, can also be evaporated, transpiration by plants, and groundwater use. So that is an ecosystem, that cartoon, and there are also some other species that depends, well, especially for groundwater dependable ecosystems, like birds, which depends on riparian vegetation, which in turns depend of groundwater, and some fish. Okay, yeah. This transition zone between groundwater and surface water, the hyporheic zone, plays an important role in some species. So this figure, this cartoon, this conceptual model, you can also model in Excel. So here is the same figure, and with some values. This is an homogeneous hydraulic conductivity, and well, the abscissa, the x direction, the delta x, the infiltration here. We have some constant infiltration, 200 millimeters per year. The water level in the river, in the wetlands, the resistance between the river and surface water bodies and the groundwater, the pumping rate of this one-dimensional well, one-dimensional well actually is a channel, and the bottom of the aquifer here, the saturated thickness, the transmissivity. And for this specific problem, I include a sea water interface using the Guyben-Herzberg approximation, and this is the interface. So there are many ways to play. Well, models can be used to analyze different behaviors. And suppose that you lower the infiltration 10%. Can be climate change, can be deforestation, and you can see here, yes. So you lower the infiltration just 10%, and for this particular case, there is an impact on the springs, probably disappears, of course, decrease in base flow, impact of wetlands, sometimes disappear the wetlands, impact on vegetation, and in general, if there is a groundwater dependable ecosystem, well, there is also an impact on the whole system. You can also, this constant head, raise the sea level, and well, I raise 4 meters just to see visually that the sea water intrusion, so you can just see the difference. And also, if you pump that one-dimensional well, there is an iterative solution, so you can see that kind of upcount of sea water intrusion in that well. So that's another simple way to analyze that kind of systems. Pumping and slug test. Well, here a pumping test is just the drawdown as a function of the distance from the observation point to the pumping well and as a function of time. This is the solution for a confined aquifer, so I use the Tice equations. If you are familiar with the Tice equation for confined aquifer, use a single formula, copy and paste. I use two spreadsheets, one for the drawdown, that is, you see here the con, and the other for the parameter u, which depends on time. Oh, let me, yes. I don't want to explain any formula, it's just the way to apply spreadsheets. And again, without any programming. Well, you need the appropriate formula, copy and paste, and use the graphics display of Excel. This is the classical solution of a pumping test in a confined aquifer. Here we have the field data, the well discharge, the distance of the observation well to the pumping well, and the time drawdown data. In this graph, the drawdown versus time. These are the data, these black points. And this gray line is the type curve for a confined aquifer that I get just from the existing textbooks reference. And this is the typical well function for a confined aquifer. You can use for a semi-confined water table, partial penetration. And it's the same approach as we did more than 30 years ago, but here with the spreadsheet. So you just pick with the mouse that point which is related to the other ones, and in the lower part you get the transmissivity and a storage coefficient. You can zoom in to fit the field data to the type curve. So that's it. Another way, an automatic fit. This is exactly the same problem. Here you fix the data and you get the approximation of this theoretical curve to your field data. So you have to give some initial guess. Here is the reference, Carl McEllhiney from Kansas Geological Survey. And in the lower graph, there is the difference between the theoretical calculated and the observed data. There are also some other add-ins package like solvers if you want to do some statistical analysis. But here you can see iteratively that in the approach of the theoretical curve to your field data, the time drawdown data, very often is jumping up and down, and you never get the solution, but you can see visually. In this case, you have used that factor, the relaxation factor, and well, you continue with the approximation until you get the final result of transmissivity and storage coefficient. Here is the difference between the theoretical data and the observed data. So you can use the Hunter's semi-confined approach. For example, the Newman solution for a pumping test in a water table aquifer. Again, the time drawdown data, the well discharge, and this is a typical behavior. So the early data depends on the elastic storage and the transmissivity. You can use also manually by trial and error. It's not to after 3-4 iterations you get the solution. And well, here you fit to that type curve, and you get the transmissivity and the elastic storage coefficient. And well, this flat area depends on the vertical hydraulic conductivity, the vertical flow. And well, you can see here the curve, and just type that number in the spreadsheet, and you get the vertical hydraulic conductivity and the horizontal hydraulic conductivity. And then use the end part of the curve, and you get the specific yield. Very recently, Newman improved that approach to taking into account the unsaturated flow. But, well, there are a lot of books of pumping tests. You just put the appropriate table and fix in the same way to calculate your pumping test. A slug test. Well, there are some procedures. This is the Borsleb solution. Again, the time ahead, the initial displacement, and you get the hydraulic conductivity not using that line. For example, if you use that manipulate points on the screen, with that window, you chose any of these 2 points, this point 2, and just drag. And well, it's just in less than a minute you can fit your data, and you get the hydraulic conductivity. Okay, now we are in Adelaida in Spanish, Australia Meridional. But let's go to Colombia. Here with Google Earth it's very nice. Still, I have my jet lag. It takes me 3 days to go from Colombia to Australia. And this is Bogota, Colombia. And we have here some plain, Bogota plain, the Bogota Sabana de Bogota. Okay, now there is some map, and let's continue. Yes. So this is the Bogota plain, Bogota river, and the flat area is mainly silts and clays, so not permeable. There are some local sands, but the main aquifer is a sandstone. Here are the outcrops, so there are limited recharge, and well, I don't want to show you all the structure and the complex geology, but there are some faults. Let's see some picture. Yes. So this is Bogota, the flat area, clays and silts, and the sandstone. You see here the dip is almost vertical. So there is a very big fault here, and here some fractures. That fracture, but also this is the place where I worked, University of Los Andes, the Faculty of Engineering. But let's another view, and you can see here also the depth of that sandstone. And this was a pumping test we run 30 years ago. Let's zoom in, and what I want to show you, well, we use one well and 3 observation wells, but that's the theoretical cone of influence for 1 day, 2, 5 days, 10, 1 month. And this is for one well. Now we have thousands of wells, so the sustainability issue is a big problem. There is a depletion of the aquifer. But, well, we use spreadsheets for that calculation. This is a very simple problem. Just the drawdown in the aquifer. You can include well losses, of course, with the transmissivity and storativity of that aquifer. And this is the solution for 1 day. So This is the theoretical cone of influence for 1 day, 5 days, 1 month, and so on. So that's another way to use spreadsheets. Superposition principle. Well, superposition principle is just the additive property of linear system in space and time. And spreadsheets are wonderful to work with that superposition principle. Well, this is the solution, the steady solution in a confined aquifer. Well, there are that formulas, but I will not explain that. Just that that type of formulas you just put in a single cell, copy and paste through all the spreadsheets or the area that you want to analyze. But here the parameters, of course, the hydraulic properties, but the well discharge and the location of that well. Here is well number 1. You can copy the entire spreadsheet, that worksheet, to another one and change the well discharge of that specific well and the location of that well. And you can include 2, 3, 4 for these specific problems. I have 5 wells. You can include regional gradient. Here the slope in X and Y direction. And the result that is just the sum of all the previous spreadsheets, and that's it. So that's an analytical solution of multiple wells. We use it in Bogota mainly for a groundwater, for a flower industry, that they have some wells. And you know, well, there, if they find a good well, just drill very near another one because that well produces water. So that's the way they think, you know, and it's difficult. It's completely different as we think, and that's also one way to show and to calculate, well, what is the influence of a neighbor well in the whole system. This is some procedure for variable rate pumping test. I take from a reference in the 80s, Virtue and Summers. And for this particular case, this is the same first example of the pumping test. Here, constant pumping rate, and here the recovery, 0 discharge, and the time drawdown data. That is these blue points, drawdown versus time, and the gray line is the theoretical curve. But Virtue and Summers used this dimensionless time, and here the drawdown over the discharge rate, and you can take into account the well losses. Here is an observation well, so there is no well losses, but you can take into account well losses. And the procedure is similar to the Jacob approximation, but a little bit different. For example, here you, with that line, for example, for this first part, okay, let's stop. Here you see that it fits pretty well the recovery stage, and the value of transmissivity is a good value. But you can use the entire pumping test, the pump stage and the recovery stage, and if you have more steps, you can include. And so I haven't seen that procedure in the literature of the reference, but you can use the entire data, as you can see here. The approach is until you get, well, let's say a good approach from these theoretical simulated points, Analytical, and your field data, and you get the transmissivity and the storage coefficient. I have probably hundreds of pumping tests. This is a pressure transducer in some well, the pumping stage and the recovery stage. And we advise the well owner, please do not pump the well. But no, nobody was there, so he decided to pump for 5 minutes. So, well, the pump was damaged, but with this procedure, you can include also this. So you get the transmissivity, the storage coefficient, and the well losses. No? This is the taste model also, but with a variable rate. And the last one for pumping tests, this is very similar to the first one, the taste equation. But this particular well begins at time 0. The second well, that is another pumping rate, another location, begins after 1 month, and so on. Here I have 4 wells, and well, let's move after, here is the cone of influence. After 30 days begins the second one, after 60 days, the other one after 90 days, and if you have more wells, copy and paste. So that's it. And this type of 3D graph are the built-in Excel graphics. Oh, I have one, but probably more examples. This is the also superposition in time and space for one-dimensional wave attenuation. So here, when it increased the head, the tidal, I use one spreadsheet when it's rising and another one when it's lower. And here we have the time of that tidal. So you will see here, okay, it dissipates the head in the aquifer, and after 1.2 days, it lowers again, yes, and you can see here the wave attenuation. So, well, you can also solve that type of problems. And here I combine particle tracking with superposition. So this is, I adapted this problem for a real problem, and the gradient is in that direction. And there were 3 wells, and it occurs some release in this area. You can give any color to the particles. In the Excel, I give just red, polluted or contaminated particles, and this white fresh water. And here is the gradient, the delta time. So you can see here how it's moving each particle. You can include any wells that you want. Here I lower the delta time just to avoid jumping along the well. And you can see that here that will capture white or clean particles, also this well here. But precisely these red particles or contaminated particles go to the farthest well. So that's one way to use particle tracking and superposition. And again, it's just copy and paste. I use the velocity here, the velocity field for all the wells. Here is the same approach, but including dispersion by random walk. This is a service station in Bogota. The gradient is in this direction, and the blue are clean particles, clean water. And here you have one red particle, but actually there are 100 particles in the same position. And well, they do not allow to drill a well, a remediation well, a pumping well here, but just in the corner. So you can see here the dispersion is not too efficient because you pump clean water. As here, what's happened? Okay. And well, also almost all the contaminated water were pumped, but not all the water. So some contaminated water just go to the neighbor property. And this is, we use air resistivity soundings, two-dimensional air resistivity, but also one-dimensional air resistivity geophysics survey, and mainly for groundwater exploration. So what you have here is the field data, and you measure in the surface terrain the apparent resistivity as a function of the electrode separation. And you plot here the resistivity versus the electrode separation, that is that point. And you have an earth resistivity layer terrain. This is the theoretical, and this is the response. Those who are not familiar with resistivity is very similar to the rain runoff unit hydrograph. If you change the value in the same way, change the response. It's unit systems. If you change the amplitude of the input, it changes the amplitude of the response. And for this particular example, it's 4-layer air layer resistivity. And just to show you how it works, you pick with the mouse, and you just change the resistivity and the depth of that layer until you get, well, that manual fit to that curve. So that's another way to use superposition principle. And there are, of course, a lot of more applications of this procedure. Numerical models. We have talked about numerical models, and you have many very robust numerical models, mode flow, fee flow, but here is just a way to copy and paste with the proper formula, as we show in the first slide. And let me see how a two-dimensional model is constructed. Here is built. No flow boundary here, and a constant head boundary in an homogeneous aquifer, two-dimensional. So the head in each cell is just the mean value of the neighbors, the left plus the right, up and down, and use copy and paste through the entire domain. And you can, what's happened here? Okay. You can, here I will put 2 wells. This is the formula. I don't want to explain in detail, but it's very simple algebraic formula. The well discharge divided by 4 divided by the transmissivity, and here another well. So the same formula. Here the well discharge rate divided by 4 divided by the transmissivity. And you began to iterate. So that's it. So, well, after some iteration, you can just press the button F9, and then you end up with the result, and that's it. So we construct in a minute a two-dimensional, of course, very, very simple model. But here you can see the surface head, the potentiometric head. And also another feature of Excel 2003 is that you can pick, you can do that also in Excel 2007, but you have to work. But I don't know what they didn't maintain that property, but you can pick one of the corners and just drag and see from below, it's it is very simple. I still use the Excel 2003 here, out of course the Excel 2010 and so on. Some example of water management from pre-Inca times. This is a project with the Department of Anthropology at the Universidad de los Andes. They are interested in many features about and also about water management of pre-Incas. And these are some terraces of pre-Incas. And of course, surface water is still, they have that channels. But groundwater, there are all terraces. And Incas learn from pre-Incas. This is Machu Picchu, so they use these terraces for drainage, for erosion control. And this is a short video from National Geographic. You can see the entire video from YouTube. And some of the excavation shows really a drain in that terraces to evacuate the rain, the infiltration, to maintain the humidity in the soil for crops, and depending on the fractures of the bedrock, sometimes evacuate the flow through the bedrock, but also they have some drains. We are at the early stage of this project, but spreadsheets can be used to analyze. So anthropologists now, they learn how to use spreadsheets. You cannot construct monitoring wells or boreholes in that terraces, but here just to figure out how much water can evacuate but drainage each terrace. The rainfall in Machu Picchu is about 2,000 millimeters per year. So here with some hydraulic conductivity, the resistance with the bedrock, well, we have many scenarios, but for this particular well, we increased the infiltration, so you can see here the movement of the water table in that terrace. So sometimes they put the drain here, and of course can evacuate more water to the next terrace, and so on. Let me show one example of the use of spreadsheets. Of course, in Santa Marta, this is a Caribbean city in Colombia, and well, this is an alluvial aquifer surrounded by granitic rocks, impervious, and this is the Manzanares River, and some of the water of the Manzanares River is lost to the sea. So we developed a project for artificial recharge to infiltrate part of the flow of the Manzanares River. This is some picture, the aquifer and the granitic impervious rocks. This is some general cross-section, so this is the morphology of the bedrock that prevents seawater intrusion. So some of the water from Manzanares River is lost to the sea, so we developed some project to infiltrate part of the flow of the Manzanares River, some of the hydraulic parameters. This is the Manzanares River in a non-rainy season. When it's a rainy season, well, it also overflows that channel. And well, this very old-fashioned rig, well, I put that picture because we revealed with the students, so they were very proud. We bought that rig at $4,000, and we drill like 90 boreholes, and then we sell with the same $4,000. But And well, of course, the municipality just drilled some with some new equipment, much boreholes. And we install piezometers in the stream bed. Well, there are some safety issues here, but you know, well, this is one of my best students, Flavio Bonilla, now deals with nanotechnology, transport of viruses. But well, sometimes you have to include the resistance or the conductance of the riverbed, and very often you just pick from the surroundings. And so here it's with this hand auger, you can install boreholes and to measure the infiltration. And this was the final conceptual design, 2 concrete dams, and in between sandbags, just to evacuate the peak flow. So it is very manual. And we construct the first structure, and the municipality other. Also some infiltration wells, but they were not too efficient because the head is not too high. But, and we took that idea from the Santa Ana River in the California. They use inflatable dams. We use sandbags. And this is a Google Earth. No? Well, there are here the freeways. You can see here when you approach the coast, there is zero outflow. They infiltrate near 24 cubic meters per second. We infiltrate half cubic meter per second. But it works, a lot of labs, experiments, and infiltration, some fractal behavior. Professor Carlos Puente from Davis also analyzed that behavior. And some in situ infiltration tests. And well, that's the recharge system, the conceptual design, the lab models. Here the recharge structure, and here also how it operates. And of course, the spreadsheets. It was like 20 years ago. At that time, we used it was not Excel, it was the Quattro and the, oh, I forgot that. But now with the students, well, this is a two-dimensional model. And of course, the river, here, there are some blue points here that are the walls. And this is the Excel also, the river, and the structure is located more or less in this area. And this is one of the scenarios we model. So you can superimpose the Excel graph over a map. And well, you can draw here the flow lines from the river. So also that's one application of a spreadsheet. And this is a time dependable. This is an alluvial fan in Ecuador. Here is the sea. And you can see here all the pump points in 2D and 3D. And this model includes the Geiben-Herzberg approximation for seawater intrusion, and some of the wells near the coast were just contaminated by seawater. So that's another application. Subsidence. These examples are well located in Mexico, and I try to fit at the same scale all these pictures taken at different times. This particular well were drilled in 1938, and you can see here the well going up. So what really happens is that the terrain is sinking, it's subsiding, so the visual effect is that the well is going up. And is located, that particular well, in the Comisión Nacional de Aguas, National Water Commission. And here is my friend who provide the picture, Daniel Arcos. And well, in these 2 years, from 2010 to 2012, well, it sinks a half a meter, so it's still sinking. The whole, you can see here, I can't remember, but it was like 8 meters or 9 meters. And you can use spreadsheets. I use a vertical finite-difference spreadsheet every 3 meters. And Mexicans use first a shallow aquifer, that is this blue color here. And I have the head at time t, the head at time t minus 1, and what's the change, the compression or the subsidence per each finite difference. And here some of the geotechnical parameters. And here the head as a function of the depth. And well, first, in the first year, well, they lower, of course, the head in this part of the aquifer, but the head, the pressure dissipate through the clay deposits, as you can see here. And in this graph, they subsided as a function of time. And then, after some years, began to use the second deep layer, this one. And of course, it dissipates and is still going down the subsidence. And well, that's one way to model a transient one-dimensional flow and also one-dimensional subsidence. You can see the wall on the left that is going up. So this is just to simulate what is happening there. Flow system analysis. Let's continue. Flow system analysis. Well, Joseph Todd was the father of the flow system analysis. And here we solve numerically the flow through a cross section. And what he did is no flow boundaries in this cross sectional and superimpose an undulated water table in an homogeneous aquifer. So with these boundary conditions, and this is a constant head for the head, you can use also the dual problem for the flow. And again, use the mean value of the neighbors. So to analyze the local flow, the intermediate flow, and the regional flow. This is the same problem, but here I put some particles on the recharge areas and some reverse backward particle tracking. So you can see here, I use one spreadsheet for each particle, and you can see, well, different travel times, very low flow paths, some more fast, and also some particles that reach the stagnant areas, like this yellow area. So to analyze wetlands, okay, vegetation, phreatophytes, you can see here a fresh cold spring. Here a saline warm spring. In fact, Professor Gleason from the University of McGill finds springs by measure the temperature. And many other features is the redox potential, oxidizing, reducing, ion exchange, accumulation of total dissolved solids, temperature, and so on. Here is an example again at the Savannah, Bogota, where we have some faults, and the aquifer is this green, and here some semi-pervious, well, not too permeable layers. We have here a shale and some faults, and this is the solution for the head, and again with the particles, just to show you very rapidly how it works in the Bogota River. That's the blue particles. Well, the flow comes from the neighbors, but you can see here that there are hundreds of years. And the travel time from the recharge area to the center of that basin, it takes thousands of years. And it is in agreement with the project of University of Waterloo, Professor Ramon Aravena, with isotopic measures. They find that is thousands of years, the travel time from the recharge area to the center of the basin. Groundwater contamination, I have shown you some examples, but let me show two more examples. This is an analytical solution of one-dimensional contamination. Here some release of 400 micrograms per liter ppbs, and well, you can see here the natural attenuation. Also some other graphs that you can use in Excel. And well, this is just without mechanical dispersion. And again, copy and paste. And you can see here the movement to see what the concentration in your receptor well. This is a numerical example of dispersion. You can couple with two-dimensional flow, but again, here some release, the part per million, and you can see here the, well, graphically and numerically the dispersion, the natural attenuation of that problem. And many, many other applications. Let me show you a few, two or three. This is soil vapor extraction. And, well, again, a spreadsheet to design the points of soil vapor extraction, especially in service stations. The Piper diagram, the ions, the cations, and the anions. And here also the output of the ions. Many ways to put the data there. And many others. Here the Dominico solution for groundwater contamination, sieve analysis to calculate the hydraulic conductivity, well logs, and so on. Unsaturated groundwater flow, when you have a wearing front in the soil. So there are hundreds of applications. I can talk the whole week about problems, but really that's what I want to show you, and just to emphasize that it's really a very, very good resource for teaching. And some of my spreadsheets, there is you can download. It seems that it is a Google web page, but I think we reached the maximum level. So we are now trying, my people in Bogota are trying to put that in a new web page. A few tutorials in YouTube. So you don't have to copy, just put Carlos Molano spreadsheet in Google, and it goes to that web page. And well, that's all for now. Thank you, thank you, thank you very much. So confusing. Yes, well, that's the way I use here, just copy and paste. No? But that's a way just to teach, especially for people who do not any programming. But you can combine really programming with the Visual Basic application. And well, there is also very efficient way.
I've got one. Is there a way of applying some sort of sensitivity to some of your input functions that you put into the spreadsheet as a way to give some certainty around whether you're...
Yes, well, you can use the solver package. The solver package is a statistical package, and you can do that sensitivity analysis. In fact, the automatic fit that I show you is by sensitivity analysis, just to change some delta in the parameter and to see what's the change in the output with some optimization procedure, and there are excellent programs, well, also for spreadsheets that you can optimize. But the students can use that program, that package. But the simple way is that one. The students, it's creativity goes. Sometimes my students look, professor, what I did. Okay, that's excellent. So there is not a fixed way. It's a very, very wide way to solve that type of problems. Yeah.
All right. Thanks, Carlos, for coming in.
Thank you very much. Can I present two more slides about, it's just I want to invite you to Cartagena de Indias. In fact, last year in Perth was elected Colombia for the International Congress in 2016, so everybody is invited. Cartagena is a beautiful city in the Caribbean Sea, also a historic city, and it's very nice, and the only risk is wanting to stay really, there is no other risk.